Okay, so in this video, our interest is on differentiability of functions. Like I emphasized at the beginning of the video on calculus, our interest is on functions of real variables. So when I say differentiation of functions, I simply mean how to differentiate real valued functions of real variables. So as a way of motivating this topic, so consider having a physical phenomenon of, for instance, you try to boil water, boiling of water, You agree with me that as time progresses, if you heat up water in your stove, as time progresses, the temperature of the water keep on changing, So if we try to compute the rate at which the temperature is changing over time, of course that is doable. So when we compute that rate of change of temperature of the water over time, and then we take average rate of change, then we have something. Okay, so this is one example of physical phenomenon that rate of change is important. And then it is from this rate of change that the concept of differentiation or differentiability of functions was based on. The early mathematicians that worked on this include Isaac Newton and all the rest of them. Actually, he stood on the earlier works done by his mentors to build and finalize what today we know as the formula for or the method of differentiating functions. And this method of differentiating functions is precisely what we're going to concentrate on going forward. So we start definition. Given a function, let me abuse notation and write f of x. The derivative of f with respect to x is given by the following limit. So it is the limit. Okay, I'll explain this shortly. As change in x tends to 0 of f of x plus change in x minus f of x, so divided by change in x. If this limit exists. Yeah, because it's possible to compute this limit and then it does not exist. In that case, we say that the function f is not differentiable at the point x. But if we compute this limit as delta x tends to 0, and this limit exists, that means it is a fixed number, it's a given number. Then we say that the function f is differentiable at the point x. And in that case, if that happens, we write that f prime of x is equal to the limit as delta x tends to 0 of f at x plus change in x minus f of x divided by change in x. So when this limit exists, we call it this number, f prime at x. That's precisely what I mean. But then if the limit doesn't exist, then f prime does not exist, and so we say the function is not differentiable at that point. Okay, so this is the definition. I need to explain what I mean by change in x. Like I started with the example of boiling water. By change in x, I simply means, suppose I have a starting point x, and then I consider another point x1. So I look at what happens between x and x1. This is x minus x1. So this is what I mean by change in x. That means simply the difference between the starting point and then the next point you are considering in the domain of interest, So that's what we mean by change in x. So you observe that if change in x tends to 0, it means that x is approximately equal to x1. So, but that is not really of interest now. But just have in mind what I mean by change in x. So as this happens, then compute the limit. If the limit exists, then that is true. Some authors will write this definition and say, which is equivalent to this, and say it is that f prime at x is nothing but limit as h tends to 0 of f of x plus h minus f of x divided by h. This is again a valid definition because here I simply take h to be my change in x, and then we reduce, we simplify notations, and this becomes this. So as h tends to 0 is the same as saying change in x tends to 0. And so we have this. Okay. So this is the formula given to us by Isaac Newton, and then it has been of help to compute rate of change, average rate of change, or what we call the derivative of f at a given point x. All right.